Now that we know that we have these specific allowed energy levels, these different quantized values for what the energy of our given gas molecule can be, for this set of energy levels, how do we determine what the probability of the particle occupying that specific level is, or for a collection of molecules, what the probability of the total energy being a certain value is? So the critical factor that we need in order to help determine this is called the Boltzmann factor. And it's one of the most important values in physical chemistry. So the probability for a given state I with energy EI is proportional to the exponential e to the minus EI, energy of the state, divided by the Boltzmann constant, Kb, times the Kelvin temperature, T. And this thing here, as I said, is called the Boltzmann factor. This e to the minus e over kT. Boltzmann factor. Okay, so points worth noting, like I said there, the Boltzmann factor Kb, that's just our familiar friend, the gas constant R divided by Avogadro's number, and vice versa. The gas constant R is just the Boltzmann constant times Avogadro's number. You might make the claim that the Boltzmann constant is the more fundamental unit. And this has a value, in case we look that up in a table or somewhere later, of 1.381 times 10 to the minus 23rd joules per Kelvin. So it kind of relates between the scale of temperature and the scale of energy. Because now if we have Kb in joules per Kelvin times the temperature in Kelvin, then that's going to be joules per Kelvin times Kelvin, or just joules. So kBT kind of gives us an energy scale for judging how quickly the probabilities of these different energy states are going to change. And then, as I mentioned, T, it's very important that we make sure to remember to put that in as the Kelvin temperature. Most things that we do, it's going to be important to put in the Kelvin temperature. Okay, so keeping in mind something from probability theory about how probabilities work, if you have a probability pi that the system exists in a state I, then the probability over all those states should sum up to 1. There should be a certainty that the system exists in a given state. So summing over all of the states I for the probability of every state should give us 1. And that's a condition which would be called normalization. You might remember normalization from the previous quantum chemistry playlist, where we would normalize our wave function. Here it's a similar type of thing. The wave function squared is a probability, and here our system state probabilities, we want those to all sum up to equal 1, which is certainty that our system exists in one of these given states. Okay, so if we take all of these Boltzmann factors and we sum them up, we'll get a very special function, which I'm going to call Q. So if we sum over all of these states I of e to the minus energy of the state I over kBT, then we're going to get this factor, which we are going to call the partition function. And much like the wave function contains all the information that can be known about a given particle, a partition function contains all the information that can be known about a given ensemble or a given collection of states for which are possible for a collection of molecules. And additionally, we can express this in a slightly different way, which is this equivalent, sum over I e to the minus beta EI, where we're going to define this beta quantity, define that as 1 over the Boltzmann constant times the temperature. And this beta is sometimes just easier to work with. It's pretty ubiquitous in statistical mechanics, which is what we're kind of doing here when we're using this Boltzmann factor and state probabilities and partition functions. This beta sometimes is just easier to work with than writing KBT everywhere, and sometimes it's just easier to numerically manipulate. So these two are equivalent here, and sometimes we just use beta, which you can kind of think of as an inverse temperature. Okay, so now that we've got this partition function here, that's the sum of all of our probabilities, which are not normalized yet. We can then get our final normalized probabilities. So we have the probability of the system existing in a given state is going to be e to the minus beta, energy of that state, over summing over a different index variable, say j, e to the minus beta ej. Or putting it a different way, a probability of our system being in a given state is 1 over q e to the minus beta ei. So that's our probability for the system being in a specific state, and that's just our Boltzmann factor divided by the partition function. Boltzmann factor for our individual state divided by the partition function for our whole ensemble. Now, you might also see the energy expressed as something which depends on the number of particles and the volume of the system. So if we were interested in not, say, perhaps one molecule, but an entire collection of molecules, then we could have a given number of molecules in the system and a certain volume in which they were contained. And if we did that, just rewriting this in a little bit more formal language in terms of all these formal variables, then we would have a partition function which depends on number of particles, volume, and inverse temperature beta. Generally, you'll see this written out in terms of 3 given variables, equals sum over all of our states, Boltzmann factor for each of those states, e to the minus beta ei, where the energy of the given state depends on number of particles and volume. So then if we were to write our probabilities in this kind of a more formalized way, we would have that the probability of the system being in state I, dependent on NV and beta, equals 1 over Q NV beta times e to the minus beta ei of NV. Okay, so those are 2 different ways that we can express the probability, one generalizing it to a collection of particles with number n in a container of volume V, and perhaps this might be applied to the more limited case of an individual particle or any type of other system where we're not specifying what variables this factor explicitly depends on.